When you first came across differentiation, it's quite likely that you came to think of dy by dx as just a meaningless clump of symbols that always go together and always just mean the gradient function is. So you may have had a good understanding of how to use it and apply it, and you might be comfortable finding stationary points by setting it equal to 0 and applying the process to something involving x to get the derivative of x squared or 3x cubed and so on. But we need to start thinking more carefully about what the object dy by dx really means so that we can apply it effectively in a much wider range of situations. This is the beginning of what's known as multivariate calculus, the idea of being able to differentiate with a range of different variables that may have connections with each other, but we need to be able to differentiate them with respect to whichever variable we particularly need at this point. It's called implicit differentiation for reasons that will become clearer as we go through, but the idea is we can move away from functions that are just written as y equals some function of x. So we need to think of that dy by dx as being the rate at which something changes as x changes, and in this case the something happens to be y. So in the same way that when you square root y, the result is the square root of y, when you differentiate y with respect to x, what you get is dy by dx. So it's an object that represents specifically the rate at which y changes with respect to x. And there's a lot of similarities. For instance, if I asked you to work out what the square root of 2 was exactly, well, the only precise answer you can give is a rather unsatisfying root 2. It's a symbol that represents the number which you square to get 2. And in the same way, if we don't have any other information about y, and I ask you what y differentiates to with respect to x, the best answer you can give is the derivative of y with respect to x. In other words, dy by dx. So it's an object which describes the rate at which y changes as x changes. And you can think of it as an operator that works on other things. So with x squared, you might find d by dx of x squared, the derivative of x squared. But because x squared is quite clearly a function of x, we have tools that we can use to actually evaluate that as something which doesn't have any derivative terms in it anymore. The rate at which x squared changes compared to x is 2x. What I'd like to try with these is to try to broaden your interpretation of dy by dx a little bit by differentiating both sides of the equation in each case with respect to x. If it's something which you can directly calculate, like there's an x squared in question 4, so you can differentiate it to 2x, then do so. If it's something which involves a variable that we're not differentiating with respect to, in other words, in this case y, if you're trying to differentiate y, we know that the derivative of y is just written as dy by dx. Give it a go, see what you can write down for these 6, and then when you've had a bit of a stab at it and you've tried to get yourself in that thinking pattern, then unpause the video and we'll go through the 6 answers. So we'll begin with the first one. Predictably enough, this one, in fact, differentiation is almost overkill for this if you're thinking of it in terms of here's a straight line, I wonder what the gradient of the straight line is, because that's effectively what we're being told. But on the left-hand side we have y, and therefore the derivative of the left-hand side is dy by dx. On the right-hand side, you've got something which is exclusively a function of x, 2 minus 3x. You can differentiate the whole thing, the 2 disappears, the minus 3x becomes minus 3. For the second question, you may not have noticed this, but the second and third are all describing exactly the same line, so in some sense the result should be exactly the same. But for the second question, having rearranged the equation a little bit, it's no longer written in the standard straight line format, where y equals some multiple of x and a number added together. It's now written in the alternative standard straight line format, ax plus by equals c. But we can still differentiate both sides. We just take it term by term. So on the left-hand side, 3x differentiates to 3 when we differentiate with respect to x, but y differentiates to dy by dx. And any constants, of course, differentiate to 0, just like it did before, the 2 disappears. And although this looks slightly different to the one above, it's identical. It's just been rearranged slightly. Dy by dx is still equal to negative 3. That's what 3 plus dy by dx equals 0 means. And question 3, all I've done is doubled everything. So it kind of makes sense that the result will be doubled. And if you are finding this idea of differentiating 2y a bit confusing, well, hopefully you can see from these two examples, questions 2 and 3, that the derivative of 2y with respect to x will just be double the derivative of y with respect to x. That's how derivatives work. If you know how to differentiate x squared, then you know how to differentiate 2x squared or 5x squared, because it's just going to be 2 or 5 times the derivative you've already found. And it's exactly the same when you're differentiating y. On the right-hand side, we've got a similar thing. X squared equals y. Well, it's just been written in a different way round to what you might normally see, but we can differentiate x squared to get 2x. We can differentiate y to get dy by dx. For the next one, y appears in two different places deliberately. It would be perfectly possible in this case to rearrange a bit, add y to both sides, divide by 4, and then find dy by dx exclusively in terms of x. But there's nothing stopping us from differentiating each separate part of this whole equation with respect to x. Just like with question 3, 3y differentiates to 3 lots of whatever y differentiates to, so that'll be dy by dx, and x squared on the right hand side becomes 2x. The y on the right hand side becomes dy by dx. Because we're taking it away, we're now taking away dy by dx. And if you tried rearranging question 5 so that you made dy by dx the subject, you'd get exactly the same final result as if you rearranged the equation at the very beginning of the question and then differentiated with respect to x. So although for many of these questions you're looking at now, it wouldn't be a big deal to rewrite it as y equals something, it's worth noticing that everything you've previously done would work just as well if things were rearranged in a slightly funny way. And even question 6, where I've thrown in an additional variable that I've not even mentioned before, it still works just the same. We can differentiate x with respect to x because it is x, and so it's going to become 1. But when you differentiate y with respect to x, we get this object, the derivative of y with respect to x. And z will differentiate to give the derivative of z with respect to x. So what does it mean for something to be implicit? Is that a word I'm just going to keep throwing into conversation and expect you to figure it out from context instead of telling you exactly what it means? Okay, well, that's basically what implicit means. And it's pretty much the same with differentiation. The idea is instead of spelling out for you, here is the thing and this is what it does, it's just sort of left to make sense of itself. In other words, y will appear somewhere in the equation, but it may not be in pride of place at the very beginning. You'll see what I'm talking about when I show you a few examples here. Some of these will look like the kind of functions that you're used to encountering, and you think, oh yeah, I can see what the output value is because it's right at the beginning with an equals sign next to it, and I can see what the input would be. That's the stuff that goes into the messy function on the right hand side. But not all of these are written like that. Quite a few of them have got x and y jumbled up, mixed together. So see if you can skim through them and maybe make a note of which ones you think are implicitly defined and which ones are explicitly defined. Which ones do you have a clear output value for a given input, and which ones are just some kind of mixture of the two. One nice way to think about this is if you were asked to sketch any of these graphs, in some cases, like y equals sine x, one approach you could use, even if you didn't know what the sine x function did, is to pick a list of x values and substitute them into the right hand side, and as soon as you do that, out pops a number and it gives you the value for y. Now if you try doing that with the second question, x minus 2 squared add y plus 1 squared equals 81, any number you pick for x will not give you immediately a value for y. Instead, it will give you an equation involving y that you would then need to solve. So your work will be a little bit trickier if you were trying to sketch one of these graphs. Okay, once you've decided which you think is which, you can come back and I'll reveal the answers. This one is defined explicitly. This is y as a function of x. So y on one side of the equation and a function of x on the other side of the equation. The next one, however, is an implicit function or an implicit equation because this one is a mixture of x's and y's, some function involving x's and y's, where it's not obvious what y would be when you throw a value of x into it. You'd have to do some work. I'm telling you that we can determine if the values of x and y you give me satisfy the equation, but I can't necessarily very easily give you a value of y if you give me a value of x. It's the same with the next one. X and y are mixed together in this e to the x plus y term. I'm not saying it's impossible to rearrange it. Often there are ways of turning an implicitly written equation into an explicitly written one, but it's not always particularly nice. It might be a bit messy, it might be tricky, and in some cases it may well be impossible. The next one's explicit, because we have y equals a function of x. Maybe a complicated looking function of x, but it's just a function of x on the right hand side. The next one is implicit. It could easily be made explicit by subtracting x from each side, but in its current form it's an implicit equation. Effectively, if you give me a couple of values for x and y, like 2 and 4, I can say yes, I can verify that 2 add 4 is equal to 6, so it fits the equation. That lies on the straight line in this case. And if you give me a different pair of values, like 3 and 7, I can say no, 3 add 7 does not equal 6, so it doesn't lie on the line. But if you gave me just the value of x and asked me for the value of y, I could sub in your value of x, but I'd have to do a bit of rearranging before I could find y. We have explicit, y is a function of x. Implicit, x and y mixed together, so there's a function involving both of them. The next one is also implicit because we've got cos x and cos x and sine y. It doesn't say y equals, it has a function involving x and y. The next one is x in terms of y. So if we switch around what we treat as our input and output values, then you could say this is an explicitly defined equation, but it's explicit for x rather than being explicit for y. And the last one is also an implicit function because x and y are mixed up together. Anytime you can't see y as a function of x, you're looking at an implicit function or implicit equation. So the best way to think of it is in terms of explicit is y in terms of x, and implicit is anything else. Now, a good example is when you have everything on the left-hand side and then an equals 0. That's quite a common way of writing implicit functions, but it's not the only way to write them. Anytime you've got mixtures of x's and y's where you don't have y equals something, you're dealing with an implicit equation. All right, so now we get on to we can differentiate y. We're happy that anytime you see y appear in an equation, even if it's on the left-hand side, the right-hand side, mixed in with other things, take away two lots of y, we can deal with that. But when it gets more complicated, not just perhaps a scalar multiple of y, but what if you had y squared or sine y or something like that? What do we do in those cases? Luckily for us, we've got chain rule. That will allow us to deal with any function which is a function of something which may not itself be x. If it was e to the x that was being squared or sine x that was being squared, well, we'd worry about the squared thing first, and we'd leave whatever was inside the function until later, and then we deal with whatever's inside. This is exactly what's happening here. The only difference is the thing that's inside is y rather than some function of x that we can immediately see. Y is itself a function of x. It's just not a function of x that we can immediately identify. So let's think of it as a chain rule situation for a moment, but rest assured we'll be able to find a more efficient way of doing the process fairly shortly. Let's start with this. What if we want to differentiate y cubed, but we don't want to differentiate it with respect to y, we want to differentiate it with respect to x? Well, luckily we know how to differentiate it with respect to y, so we're going to make use of that. But we're going to start by introducing this new variable so we can apply chain rule. Let u equal y cubed. So u is the thing I'm trying to differentiate, which means really what I'm trying to get to is du by dx. But what I can get from this, if I know that u equals y cubed, here's something I can calculate straight away, the derivative of u with respect to y. We know that x cubed differentiates to 3x squared when we're differentiating with respect to x, and that means that t cubed will differentiate to 3t squared when we're differentiating with respect to t. And y cubed will differentiate to 3y squared if we're differentiating with respect to y. And remember, we're looking for the derivative of y cubed with respect to x. And since u is what I've chosen to call y cubed, I'm looking for du by dx. And it's just going to be a connection between du by dx, du by dy, and the one missing link, dy by dx. We can get du by dx by starting with du by dy and multiplying by dy by dx. You can see that the dy's cancel, just like we did when we looked at parametric differentiation, and just like happens in the standard chain rule pattern that we followed before. The last thing to do is to replace du by dy with 3y squared, because we've already calculated that, But although this may not seem very satisfying, this is what we're looking for, 3y squared times dy by dx. So we've got the derivative with respect to y, sort of its natural derivative. If I give you some horrible function like sine x, like sine y, for instance, you can differentiate that with respect to y, you get cos y. But then in order to turn that derivative into a derivative which is with respect to x, you'd have to multiply by the adjustment factor that we dealt with during chain rule, the derivative of whatever that function was that we were interested in. In this case, the derivative of that y. Y is like the inner function in the y cubed composite function. It's a y on the inside and it's something cubed on the outside. 3 lots of the something squared is how you differentiate the whole thing, and then you multiply by the derivative of what's inside, which in this case was just y. So 3y squared, and then multiply by the derivative of y with respect to x, dy by dx. And that's how you leave it. You have y cubed, you differentiate it with respect to x, you end up with 3y squared, which is its derivative with respect to y, multiplied by dy by dx, which adjusts that derivative to make it a derivative with respect to x. So in general, this is how you differentiate any function of y. You differentiate it with respect to y. That's what f dash of y is suggesting there. If you've got a function of y, find its derivative with respect to y, but then multiply it by dy by dx, the adjustment factor. Let's now have a quick look at how this helps us. Under what situation would you find yourself needing to use implicit differentiation? Well, we're going to start with the very first implicit function you probably ever saw, which is this. In fact, you didn't even answer the same sorts of questions with this that you did with other equations that you've looked at. If you have a quadratic, you can differentiate it and use that to solve problems involving tangents and normals. But with circles, you had to resort to a slightly more geometric approach, thinking about radius lines and the normal to a circle in order to work out the perpendicular tangent to a circle. So previously we've not been able to differentiate this, but now we can. We've got the tools because we can differentiate each part of both sides of this equation implicitly. That means instead of starting with y equals something and ending with dy by dx equals the derivative of that something, we're going to have both sides of the equation being differentiated with respect to x and not worrying about the fact that y appears in various different places throughout the equation. X squared will differentiate to give 2x. Y squared differentiates to give 2y if we're differentiating with respect to y. So if we want to differentiate with respect to x, we get 2y, but then we multiply by dy by dx. And then 1, being a constant, differentiates to give 0. And that's it. You've differentiated the circle equation. It tells you that 2x add 2y multiplied by dy by dx equals 0. And if you want to get a clearer sense of what's happening, it's often helpful to rearrange to make dy by dx the subject. This won't automatically happen like it does with explicit functions, but it can usually be done relatively easily, because anywhere dy by dx appears, it will be a factor of the term that it appears in. So you can just chuck everything that doesn't involve dy by dx on the other side of the equation, factorize out dy by dx, and divide through by whatever the factor was that went with it. In this case, that's pretty quick. We get dy by dx equals minus x over y. And now we need to think about what that tells us. Because previously, every time we found dy by dx for a function, because it's been an explicit function, the right-hand side has been a function of x alone, which means the derivative dy by dx is equal to some function of x. You can set it equal to 0 and solve it and find stationary points, etc., etc. Now what we're looking at is a derivative which involves both x and y. It might remind you a bit of finding dy by dx when we're dealing with parametrics. There's a trade-off when you have parametric differentiation in that your dy by dx term involves not x or y, but t, this new variable. But as long as you can find the values of t that make the gradient 0, you can find stationary points. You just then need to use that value of t to go back and find x and y. With implicit differentiation, it's a similar idea, but we don't have a new variable appearing. What we do have is a derivative which is defined in terms of both x and y. But we can think about this. we can see why it makes sense for a circle. Previously, when you found the gradient of a tangent to a circle, you would consider the x and y coordinates of the point you're interested in. So for instance, you might be up here somewhere. You look at the line from the origin all the way up to your point. That radius line, you already know the gradient of it because it depends on the x coordinate and the y coordinate of your point. So if you've got the point 0.6, 0.8, then it has a gradient of 0.8 over 0.6, or 8 over 6, or 4/3. And once you know the gradient of the normal, 4/3, you can get the gradient of the tangent by doing the negative reciprocal. It's going to be minus 3/4 in this case. So the point with coordinates 0.6, 0.8 has tangent with a gradient of minus 0.6 over 0.8. In other words, minus x over y. You could get any coordinates on the unit circle and plug their x and y coordinates into our expression that we've got for dy by dx, and it will give you the gradient. So it works for a circle. But it still seems a little strange that you need x and y to find the derivative. Luckily, everything you know about derivatives still works for this. If you want to find stationary points, for instance, you just set dy by dx equal to 0. And if minus x over y is equal to 0, well, that means x has to be equal to 0. And if you look at the graph where x equals 0, we're at the top of the circle or we're at the bottom of the circle. Those are the points on the graph that have a gradient of 0. Not only that, but you get a 2 for 1. You can see where the gradient is undefined. We've got a fraction, which means there are certain values for which this fraction doesn't give a valid result. In other words, dy by dx doesn't give a valid result whenever the denominator, in this case y, is 0. That happens here and here, at 1, 0 and at minus 1, 0, where the y coordinate is 0. So that's quite useful. There's a lot you can see directly from that expression, even though it may feel like it's a bit unsatisfying because it only involves a mixture of x's and y's instead of exclusively one or the other. Just for comparison, for those of you who are still determined to rearrange everything, turn it into an explicit function, and then differentiate it all from there, this is what happens if you do that. The first thing you have to do is get the explicit form, which is not particularly pretty for this equation. You have to subtract x squared from both sides, and then you've got to square root both sides. I've written it as a power of a half, so we can use chain rule to differentiate it in a second. But we've also got to remember there are two different possible square roots, because if y squared is 1 minus x squared, then y could be either plus or minus the square root of 1 minus x squared. We can differentiate it, although understandably it's going to look a little confusing. We're bringing the half down in front and reducing the power by 1 because it's something to the half, so a bit of chain rule in there. Treat it as a something to the half, becomes half of something to the minus a half. And then I multiply by the derivative of what was inside. Well, that was 1 minus x squared. So the derivative is minus 2x. And that's the bit we multiply by on the right-hand side as our adjustment factor. But of course, we still have this plus or minus at the beginning because that was there before. Now, we can go a step further and we can see that the derivative is going to have to be minus x over plus or minus root 1 minus x squared. The reason I'm writing it like that instead of putting a minus plus at the beginning is that we can then see more clearly how it links to the derivative we already found involving x and y. And maybe you can see why getting the derivative in this form doesn't necessarily tell you more or give you an easier job to do than in the format that we've already seen. Minus x over y is in many ways much simpler to work with and to interpret than minus x over plus or minus root 1 minus x squared. I hope you can appreciate that. So in general, implicit differentiation, once you get the hang of it, is much, much quicker than attempting to rearrange to find an explicit form and then differentiate from there. The little trade-off that we have to deal with is that you'll have an expression involving x and y. And that can make things sometimes a little more confusing. But the thing to remember is you're not stuck with just some equation involving x and y. If you're trying to find stationary points and whatnot, we got lucky here because the numerator just involved x. Sometimes you'll have x's and y's, but we're going to see what happens in those situations later on. We're going to make use of the fact that we already know points that we're dealing with are on the curve. So effectively, we've now got two things we can work with: the derivative, or the differential equation, which is an equation involving a derivative, and the original equation, the x squared and y squared equals 1. With both of those things to work with, regardless of the fact that the derivative has x's and y's involved, you'll be able to answer any question you need to about tangents and normals, etc., etc. So now let's look at what happens if we bring in a few of the more sophisticated rules. We've come up with lots of ways to combine functions, and remember, even if the functions look complicated, in fact especially if the functions look complicated, you'll be better off using implicit differentiation rather than rearranging in most cases. There are various questions where you would be welcome to use whatever method works the best. I've seen exam questions where some students choose to rearrange, divide through, and use quotient rule, and other students use implicit differentiation straight away. Usually implicit differentiation is a bit more efficient, but as I always recommend, use the method that makes the most sense to you once you're in an exam. At this point, you want to devote a significant amount of time getting to grips with implicit differentiation because it's a really, really useful method to make sense to you. Let's have a go at these 4 questions. And remember, wherever you come across anything where you might need to use chain rule, product rule, or quotient rule, you can. I recommend you pause in a moment and try each of these out for yourselves before you watch the solutions, and then the solutions will make a little more sense to you. Remember, any of the rules that you've already come across, they already apply. The trick is anytime you have to differentiate anything involving y, we multiply by dy by dx. That's the adjustment factor that comes in because you're dealing with a function of y instead of a function of x. Okay, let's start with the first one. X equals y squared. It's a common enough looking function, apart from the fact that x and y are a different way around to what you would expect. But if we differentiate with respect to x, x becomes 1 on the left hand side. Y squared turns into 2y dy by dx. In other words, y squared differentiates to 2y if we differentiate with respect to y, and then we multiply by the adjustment dy by dx. Question 2, this is a product. It's a product of x and y. So we're going to use product rule where we have u v dash plus u dash v. In other words, x multiplied by the derivative of y plus y multiplied by the derivative of x. So each one will appear as its differentiated version and its undifferentiated version. And this is one of those special cases where y may appear somewhere without a dy by dx immediately next to it. X multiplied by the derivative of y, and then the derivative of x multiplied by y. Of course, the derivative of x is 1, and y appears on its own there because we didn't need to differentiate it for that particular part. We were using the bit of product rule that keeps y the same and differentiates the x. And on the right hand side we have a constant which differentiates to 0. For question 3, a nice approach here is quotient rule. So we have the bottom multiplied by the derivative of the top, and you'll notice with that very first term, the y there, we didn't need to have a dy by dx because we weren't differentiating the denominator, we were just writing it down. We differentiated the x, so it's y times 1 minus the top times the differential of the bottom, x times the derivative of y, but with respect to x. One way to think of this is, how does y differentiate with respect to y? Gives a 1, and then we multiply by dy by dx. Alternatively, y differentiates to dy by dx. And then we divide by the bottom squared. And again, dy by dx doesn't appear there because we're not dividing by a derivative of anything, we're just dividing by the original denominator squared. And the right hand side differentiates to 0. Question 4 looks the worst by far, and there's a few little tricky bits to remember in here. I'm hoping, for your sake, that you will have made a mistake here or there with chain rule, and it'll remind you to watch out for some of these sneaky things that appear. So 4x had 1 in a bracket squared. You might have even decided to expand it out to be on the safe side, but it's usually quicker to apply chain rule. So we bring the 2 down in front, we think of it as something squared, which becomes 2 lots of 4x had 1 to the power of 1. But then we also multiply by the adjustment factor, which is the derivative of 4x plus 1, and that's 4. So we have a 2 and a 4 at the front of that, which gives us 8 lots of 4x plus 1. The next one is the same kind of thing, and it's easy to get a little worried about this and try to second guess and overthink where the dy by dx belongs, but we're just going to take that entire function of y, which is 3y minus 2 all to the power 5, differentiate it with respect to y, which will involve chain rule just like the previous term did. So we'll have 5 lots of the bracket to the power 4 multiplied by the derivative of the bracket. And all of that gets done first. So we get 5 lots of 3y minus 2 to the power 4 multiplied by 3. That gives you the 15 lots of 3y minus 2 to the power 4. And now you've completely differentiated that term with respect to y. You can then multiply the entire thing by dy by dx. And that allows you to turn it into a derivative with respect to x. And finally, on the right-hand side, we have sine y. It's just a function of y, so we differentiate it with respect to y to get cos y, but then we multiply by dy by dx to convert it into a derivative with respect to x. A few points to make here. To start with, you only ever multiply by dy by dx if you have differentiated a function of y. So y can occasionally appear within a differential equation, within the result that you get after you've differentiated. It might appear without any dy by dx's next to it, but anytime you do differentiate a function of y, you multiply by dy by dx. Next, like we saw with the previous question, it's often helpful to rearrange to make dy by dx the subject. This will be useful if you're trying to identify stationary points potentially, if you're trying to get the gradient at a particular point so you can find the equation of a tangent line, etc. It's not always necessary, and if you've got something particularly complicated, you might find there are more efficient ways of using the information you're given. It's a case of having to choose between rearranging and then substituting, or substituting then rearranging. Often in those cases, you want to substitute first and rearrange later. You'll see an example of that shortly. Next, this is a very helpful trick. If you're looking for stationary points, you could waste a lot of time rearranging this big messy chunk of algebra so it says dy by dx equals something. But after you've done all of that rearranging, you're just going to set that thing equal to 0 because you want stationary points. Why not set dy by dx equal to 0 straight away? Everything that dy by dx touches will disappear. The Midas touch of dy by dx. So this entire term here, that's going to disappear if dy by dx is 0. And all of the right-hand side is going to disappear if dy by dx is 0. And once those two things have gone, you're left with a very straightforward equation to solve. And immediately you can see, even though this equation is so hideously confusing looking that you can probably, you'd take a bit of time to figure out what on earth is going on with the graph of it. I certainly would struggle to jump to, oh yes, I can sketch this. Here you go, nice and simple. I'd cheat and I'd use GeoGebra, which is exactly what I did. It's a beautiful looking graph. And it does have a stationary point at x equals minus a quarter. I'm not sure it's possible to solve directly to find the y coordinate of that stationary point. I'm going to guess it's 1. And if you have an idea of what you think it is, you could perhaps verify that, but you're going to struggle to get an exact value for this because of the kind of equation it would turn into. But we can solve to find stationary points fairly quickly if we replace dy by dx with 0 before we attempt to do any rearranging. There's a few questions you can now try from exercise 9H in the textbook. You can have a go at questions 1 and 2 as well if you want some extra practice on this before you move ahead. They're all useful to work on, and there's various related questions in the mixed exercise as well. We're going to do a few more examples next. So let's try question 9 from the textbook. It looks a bit nasty. It's got logs on both sides. It's got x's and y's all over the place. And there's a couple of things that you can do here to make your life a bit easier. If you want to, you can apply some log rules on the left-hand side. ln of y squared can turn into 2 ln of y. But the method I'm going to show you doesn't assume that you've immediately recognized that. We're just going to work through as if you were applying the differentiation rules as you normally would. You might find that there are sometimes more efficient approaches that you don't notice till after you've solved the problem, for instance. Here they're asking for the gradient of the curve at a particular point. So we know we're going to need dy by dx, and we're interested in the value of dy by dx. We want to know what dy by dx will be when x equals 4. So let's start by finding an equation that involves dy by dx. It's not going to be particularly feasible to turn this into y equals something, and unless it's written as y equals something, you want to be thinking in terms of implicit differentiation instead anyway, as a general rule. So let's start with the equation, and let's differentiate both sides with respect to x. The left-hand side is the one where we're going to need to incorporate a factor of dy by dx. So let's think about how we differentiate ln of y squared with respect to y first, and then we'll multiply by the adjustment factor. Well, as we mentioned, you could turn this into two lots of ln y, which would make your life a bit simpler, but there's nothing stopping you from thinking of it as ln of something, which differentiates to 1 over the something, and then multiplying by the derivative of the something. So that's what I've done here, because it's likely a number of you would have done the same sort of thing. 1 over the thing inside, which is y squared, multiplied by the derivative of what's inside. That's how chain rule works. So we get 2y over y squared. And then because it involves y and we need it to be a derivative with respect to x, we also multiply by dy by dx. And on the right-hand side, this is also a little complicated. You've got product rule involved because we've got a half x multiplied by ln of x minus 1. The half doesn't need to bother us. In fact, if you like, you can pull it out as a common factor. You could even double both sides at the very beginning before you begin the process. But I'm going to leave it in there, and I'm going to treat the two terms separately as half x, that can be the first term I look at, and ln x minus 1 can be the second term I look at. So each of those will be one of the terms that I deal with when I do product rule, and half x will appear either in its original form or differentiated, and similarly ln x will appear either in its original form or differentiated. When you differentiate ln x, you get 1 over, when you differentiate ln of x minus 1, you get 1 over x minus 1. ln of anything differentiates to 1 over the anything. We just need to remember to multiply by the derivative of the anything. In this case, the derivative of x minus 1 is just 1, so we're good. Now there's a bit of simplifying you can do, but I'm not going to do that. Instead, I'm going to jump straight to substituting x equals 4 into the original equation, not even the derivative. I've got something involving dy by dx, and now I'm just going to leave it hanging there for a minute and go back to the original equation, because I can see that in order to find dy by dx, I'm going to need to know not just x, but x and y. I've got a differential equation, an equation involving derivatives. It's got some y's and dy by dx on the left-hand side, and it's got x's on the right-hand side. So in order to turn that into something that can give me dy by dx, I need x and y. And the way we find the value for y is by taking the value of x that we were given, x equals 4, and putting it right back into the original curve, because that will allow me to solve and find y. So there we go, ln of y squared equals half of x, which is 4, multiplied by ln of x minus 1, which is 4 minus 1. Remember, even if it doesn't say this, we should always keep answers as exact values. So in this case, we've got 2 ln y, I have used the log rule there, and 2 ln 3. You can rearrange in whatever way you like here, but however you do it, you should end up with y equals 3. And even though there were logs involved, they were on both sides, which meant that your final answer came out as a fairly nice one. So now we've got y equals 3. We've got a value for x and a value for y. We can make use of our value for y and our value for x, and now we can go back to the differential equation. We'll put those two numbers into here, and I'm doing that before I even attempt to rearrange again. It's often helpful to put numbers in first, then simplify if you can, and then rearrange. So the 2y over y squared is of course just 2 over y, and I've got 2 over 3. On the right hand side, wherever x appears, I've replaced it with 4. And then we do some simplifying. That fraction sorts itself out a little bit, and then we can multiply through by 3 and divide through by 2. And we get dy by dx equals 1 plus 3/4 of ln 3. And what we do at the very end of every question is always go back and ask myself, what was the question asking for? Find the gradient of the curve. Have we done that? At a particular point, at the point where x is 4, yes, we've made use of that, and give your answer as an exact value. And this is a nice exact value. You could go to a calculator and crunch out some decimal, but that's not what they're looking for, so I'm not even going to try it. So the thing to remember from this one, you can often save yourself quite a bit of time and potential error making steps if you substitute values into the differential equation first and then do the rearranging. Be similar with Suvat equations in mechanics. Often it's better to use the standard format for the equation and then substitute the numbers in and then rearrange, because then you'll be solving an equation with a single unknown rather than rearranging a formula with 4 unknowns, before substituting numbers in. It's personal preference in some ways, but it can often save you some time. Now there's a few more questions that you can have a go at. We've done question 9. You can go back and try question 8, and then 10 and 11 from 9H. They should be pretty suitable. And then we'll have a couple more examples. So this next example is designed to show you what happens when you get stuck with dy by dx. You're trying to find the stationary points on this curve, but we end up with something that doesn't actually tell us where the stationary points are. So let's see what I mean by that. Firstly, you've got this big scary looking creature, x squared add 2y squared minus xy plus 3x minus 5y equals 24. It looks weird, it looks complicated. It's something called a conic. There are a range of curves called conic sections. You can look them up if you're curious. Conic because you can make them by slicing a cone with a straight cut. Now if you slice a cone in a certain way, you can get a circle, so a circle is a type of conic, but if you do it slightly funky angle, you can end up with an ellipse, and there's a couple of other cool things you can get as well that you'll learn about if you do further maths. But for now, we don't need to worry about what it is, we just need to be able to differentiate both sides with respect to x. So we do the same thing we've done before. Each term that is just a function of x doesn't need any special treatment. So if you see x squared or 3x or even a number like 24, they're going to be nice and straightforward. They do what they've always done. They differentiate with respect to x. You get 2x, you get 3, you get 0. The bits involving y, we need to be a little more cautious of. So if we've got a minus 5y, we're going to get minus 5 dy by dx. We've got 2y squared, we're going to end up with 4y dy by dx. And the one you want to be most careful of is xy. That one is going to involve product rule because it has two things multiplied. So let's try it. X squared becomes 2x. 2y squared, 4y dy by dx. I'll skip ahead and do the other bits first. 3x becomes 3, minus 5y becomes minus 5 dy by dx. 24 becomes 0, and the sneaky product rule bit in the middle becomes x times the derivative of y plus y times the derivative of x. So x dy by dx plus y times 1. And that is it. That's our differential equation. The next thing I'm going to do is not attempt to rearrange it and get dy by dx equals. They haven't asked for that, and we don't need it. What we care about is stationary points. So let's look for stationary points. They are points where dy by dx is 0. Luckily for us, that means there's a bunch of things in here that are going to completely disappear. Anywhere where dy by dx appears, it's going to cancel out if dy by dx is 0. And we're left with a fairly manageable little chunk. We have 2x, and then we're taking away y, that was in that bracket that I constructed for the xy product, and adding 3. All well and good. The only problem is we haven't found the coordinates of the stationary points. We'd be expecting things like x equals 2 or 3, or x equals minus a half, or x equals 7. Whatever it might be, we'd expect some values of x to jump out as coordinates of stationary points. And yet we haven't. What we've found instead is an equation that involves x and y. So how does that help us? Well, rewriting it a little bit, you can see this particular equation is actually a straight line with gradient 2, intercept 3. That still doesn't seem to help much. What are we saying? That the stationary points lie on that line, but surely it can't be the entire line. That wouldn't make sense. Well, what else do we know about the stationary points? Apart from the fact that the gradient needs to be 0, and apparently the gradient is 0 provided y is equal to 2x add 3, but also the points are points on the curve. And that's something which is so subtle, it's very easy to miss. These are points that are on the curve. In other words, they satisfy the curve equation. Yes, they satisfy the equation for stationary points, but in addition to that, they must simultaneously satisfy the curve equation. In other words, you can solve simultaneously. All you need to do is find a way to combine what you know about the curve with what you now know about points that happen to be stationary points. And usually, when you're dealing with simultaneous equations, when one of them is as complicated as this, you're going to want to use substitution. So that's the reason I've rearranged my dy by dx equals 0 equation to give y in terms of x. That means we can now go right back to the original curve, replace every instance of y with 2x add 3. Wherever y appears, I put in 2x add 3. And yes, it's messy. Yes, it'll take a little while to crunch all the way through. Be careful with your rearranging. But if I've done this right, hopefully you'll get 7x squared add 14x minus 21 equals 0. We can simplify that down. You can use a calculator to find solutions if you like. And we should find that we get x equals 1 or x equals negative 3. Finally, by incorporating the information from dy by x equals 0 and the original curve simultaneously, we have now found the x coordinates of the stationary points. And we're nearly done. We just have a little more work. We'd want to go right back to here again and look at how we can find y values that correspond to those x values. And if x is 1, then y will be 5. If x is minus 3, y is minus 3. It's important that when you're solving simultaneously and you've got multiple solutions, you know which y value goes with which x value. Otherwise, you'll have the x coordinate of one point combined with the y coordinate of an entirely different point, and it won't match what you're looking for at all on the graph. But now we have our points. We know where our stationary points are, 1, 5, and negative 3, negative 3. Finally, this is what the curve looks like. I mentioned this, the conic section. This one is a particularly weird looking thing because it's not nicely symmetrical about the x or the y axis. That's why there's that weird xy term thrown in there. If we get rid of that one, then it becomes a bit more symmetrical around the standard xy axes, but we've thrown in some sort of rotation, so it's doing interesting things. But you can see the points we're interested in, the point 1, 5 and the point minus 3, minus 3. They are stationary points. They're points where the gradient is 0. And if you wanted to find points where the gradient was something else, all you need to do, instead of replacing dy by dx with 0, is replace dy by dx with something else. A good question that's similar to this is question 6 in exercise 9H. So you can give that one a go now if you like, before our final example. And the last example we're going to look at today is two tangents crossing. This is a bit more abstract. It's very good preparation if you're going to be doing further maths, because we do things like this when we get to conic sections. Also useful if you're preparing for STEP or MAT. You'll find questions that require a little more abstraction, where you're looking at more than just a single object. You're looking at a few different things. This is a good sort of warm-up to those kinds of questions. So we start with an ellipse, similar to the previous one that we saw, but this one has a slightly more straightforward looking equation. We're asked to find the point where the tangents at x equals 2 cross, which seems a little confusing, but if you remember, we're dealing with an ellipse and they've not specified a particular point, they've specified an x coordinate. In other words, there should be a couple of different places where x equals 2. So here's how we begin. As with previous examples, we're interested in finding gradient. That's what the whole tangents thing is about. If we want to know about tangents, we're going to need something involving dy by dx. We don't have an explicit equation, so we're going to differentiate implicitly. 16x squared is a nice straightforward bit because that is just something involving x, and the 144 just involves, well, it's even simpler than x, it's just a constant. So both of those can differentiate with respect to x very straightforwardly. 9y squared, this one's the bit you're going to be a little more careful of. With 9y squared, that's a function of y, so we end up differentiating it with respect to y initially, and then multiplying by dy by dx. We can rearrange our equation now to get dy by dx if we want to, and in this case that's probably going to be helpful because it gives us a nice efficient way of finding the gradient that we need to generate the equation of a tangent. But it's not enough on its own because x and y both appear in my dy by dx expression. So I'm going to need to find the corresponding value, or values in this case, of y. We can do that by going back to the original equation and seeing what happens if we substitute in x equals 2. So 16 lots of 2 squared add 9y squared equals 144. Do a bit of rearranging and we get y equals plus or minus 4 root 5 over 3, some awkward surd. But those are the two values of y for which x equals 2 on this ellipse. You might want to try visualizing an ellipse. Just imagine drawing yourself a stretched circle and thinking about what happens when x equals 2. it's quite plausible that there'll be two places on that ellipse, one above the x-axis and one below, where the line x equals 2 crosses the ellipse. So there are two places on the ellipse with an x-coordinate of 2, and their y-coordinates apparently are 4 root 5 over 3 and negative 4 root 5 over 3. But those two y-coordinates will contribute to two different gradients. So that's the next thing we do. We take our x value of 2 and our y value of either 4 root 5 over 3 or minus 4 root 5 over 3, and we throw those both into the differential equation, dy by dx equals minus 16x over 9y. That simplifies down a little bit. You'll notice something weird has happened with the plus minus sign. Because it was minus 16x over 9y, that effectively flips the plus and minus. Now, a good way to avoid any of this uncertainty and confusion is to just treat it separately. Right from the time you get two different y values, you set up two different equations. You find the x and y value for a single point and the corresponding gradient. Then you find the tangent line for that point. You do the same thing for the other one. But just like with coding, it's tempting to want to have something a bit more efficient that uses fewer lines and you don't need to repeat yourself so often. So if you're careful, you can incorporate a plus minus sign into your equation and do quite a lot of the working out with it. But if you have the negative of plus or minus, it becomes minus or plus. Just like in the cos A plus or minus B formula, you end up with cos A cos B minus plus sin A sin B. Because although the signs alternate, when one of them is plus, the other is minus, and vice versa. What this is telling us is, if you're above the x-axis on your ellipse, the gradient is negative. And if you're below, if you're at y equals minus 4 root 5 over 3, the gradient is positive 8 over 3 root 5. And if you've got yourself a rough sketch diagram, that will make perfect sense. You're thinking about where on the ellipse you're going to be and what the slope would be. If you're above the x-axis, you're at the top of the ellipse, it's going to be sloping downwards on the right-hand side and upwards if you're below the x-axis. You'll see when you draw a diagram. The next thing we can do is create the tangent lines. The numbers are messy, but we're just substituting into the standard formula y minus y1 equals m brackets x minus x1. We're taking away plus or minus 4 root 5 over 3, so I've done it as y minus or plus 4 root 5 over 3. And on the right hand side, the gradient is exactly the gradient that we calculated over here. So we sub that in there for m. And then we've got x minus the x coordinate of 2. The next thing I'm going to do is solve simultaneously. We're asked for the point where the two tangents cross. Go back to the original question, the point where the tangents cross. In other words, now I've found the equations of the two tangents, I need to figure out where they cross. Now there are some clever things you can do with this. You might, if you've got a diagram already, you might have a pretty good idea of one nice bit of symmetry you can take advantage of. But even if you don't, we can still apply the standard approach to simultaneous equations, and although they look messy because of all the surds, there's a lot that's similar about them, which means some kind of elimination method is going to work pretty well. In fact, what I'm going to do is add the left-hand sides and add the right-hand sides, and that will eliminate practically everything. Y plus y will be 2y, but the plus and the minus 4 root 5 over 3 will cancel out, and the plus and the minus 8 over 3 root 5 times x minus 2 will also all cancel out, which gives us a very nice result. And if you think about it, when I got to this, I went, oh yeah, of course it is. It's obvious now, in hindsight, because we're dealing with 2 points that are perfectly symmetrical above and below the x-axis. We're dealing with an ellipse, which is a stretched version of a circle, stretched horizontally and stretched vertically by various different scale factors. It's actually a horizontal stretch of scale factor 3 and a vertical stretch of scale factor 4, which may be a little confusing to see from the format that it's in now, but that's what's happened to it. When you apply those stretches, you still get something which is symmetrical about the x-axis and about the y-axis. But now I've got y equals 0, I can just use substitution, go back to either of those two equations and put y equals 0 into them. And what we find is we get x to be quite a nice value. The root 5s end up combining and cancelling out for me, so I get 9 over 2. That's the x-coordinate that goes with the y-coordinate of 0, which corresponds to the crossing point of the two tangents. And there we go. For the record, this is what the ellipse looks like, stretched by a scale factor 1 in the x direction, stretched by a scale factor 3 in the x direction, scale factor 4 in the y direction from a standard unit circle. And that gives you the ellipse you're looking at. We can see a positive gradient for the point which is below the x-axis and a negative gradient for the point which is above the x-axis.